Alright guys, in this video I'm going to walk you through a couple of quick half-life problems. Remember, the concept here is that all elements will decay. That's called radioactive decay over their lifetime. Now every element has its own decay rate. No two elements decay at the exact same rate. And also, nothing can affect the decay rate of an element's specific decay rate. So, for example, we said carbon-14 will decay, half of it will decay every 5,730 years. Nothing will ever change that. It doesn't matter if it's heated or frozen, broken, smashed, whatever. It'll always be 5,730 years. So the important thing here is this, is that a geologist will look at how much of a parent isotope is present versus how much of its daughter isotope is present, meaning it'll look at how much of the original stuff it has versus how much of the stuff it turned into, and the geologist will then ratio out one versus the other to determine the age of the rock. We're kind of doing the same thing. We're not doing ratios, we're taking a much more simplified version. I'm telling you what the half-life is, and I'm giving you ages. So really the rest is the process. To start the process, I pre-made a table. We talked in class that the only thing in table that will ever change is the time. That is the only thing that will ever change in the table. In the problems, I give you how long the half-life is, and that's what I mean by time. For the first example, it says an isotope has a half-life of 2,000 years. That's the time for that isotope. In the next one, it says a rock contains an isotope with a half-life of 15,000 years. That's the half-life for that problem. And that won't change. So no matter what those times are, this half-life, the number of half-lives here in this column, the fraction of the original amount remaining won't change, and the percent of the original material won't change. That will always stay the same. So what happens then is my table will always look the same. I'll always break down by the same amount. I'm always going to lose half because it's half-life. And so what that means is after I have everything, after the first half-life, I'm going to have half of my original percent and fraction remaining. And then after another half-life, I'm going to lose another half. I'll have a quarter, 25%. After another half-life, I'm going to lose another half of that. So I'll have an eighth or 12.5%. So if we take a look and go all the way down, that just keeps on following the same trend. I'm going to cut the fraction in half every time. Every time I cut the fraction in half. Now what's the trick to be able to do the math on that, to set up your table? All you have to do is multiply the denominator by 2. Double the denominator every time and you'll be halving. And for the percent, you're just going to cut the percent in half every time. So 100% turns into 50, 50 turns into 25, 25 into 12.5, and then all the way on down the line to 6%, 3%, 1.6, 0.8, 0.4, 0.2, 0.1. So how do you work these problems? What do we do? Well, here's the deal. First example problem says that we have an isotope that has a half-life of 2,000 years. That's important. I'm going to highlight it. You find a rock that's 14,000 years old. That's important. I'm going to highlight it. How much of the original isotope is left in both fraction and percent? That question is asking is how much is left after 14,000 years. So simply, here's what we do. I'm going to add 2,000 years, and what that says is after the first half-life, 2,000 years have passed, and I've lost half of my isotope, and I have 50% of it remaining. And I'm going to keep on doing that. After the next half-life, another 2,000 years will have passed, so then it becomes 4,000. After another half-life, another 2,000 years will have passed, so then it's 6,000. And then another one, that's 8,000. Another one makes 10,000. Another one makes 12,000. Another one makes 14,000. And I'm going to stop right there at 14,000 years. Why am I going to stop at 14,000 years? Because if we go back to the original problem, it says you find a rock that's 14,000 years old. How much of the parent isotope is left? Well, here's our rock that's 14,000 years old based on the chemistry, and this is how much of the isotope is left. There's 1/128th or 0.8 of 1%. And that's it. This is my answer right here. 1/128th or 0.8 of a percent. Now, that's one of the types of problems I could ask you with half-life problems. There's another. I'm going to clear this up here real quick. And the second is this. The second says you find an isotope, or a rock contains an isotope with a half-life of 15,000 years. How old is the rock? Do you see the difference? In the first one, I gave you the age of the rock. And in the second one, I want to know the age of the rock. How do you know when to stop? Well, I tell you there's 3% of the original isotope left. That's when you stop. You keep on adding that 15,000 years until you get to 3%. Here's what it looks like. Here's my 15,000 years after one half-life. After two half-lives, I'm going to have 30,000 years. Why? Because another half-life happened. After another half-life, it's going to be 45,000. Notice that I'm adding 15,000 for every half-life. 60,000. 75,000. And I'm going to stop right there. Why am I going to stop right there? Because in the problem it says 3% of the original isotope is left. Notice that I'm at about 3%. And when I find that 3%, what I found is that the rock is 75,000 years old. That's how you solve this problem. These are the types of things you can expect to see on our exam. If you have any questions, please feel free to ask me in class.